Hi, everyone. So now I'm going to solve problems 1, 3, and 4 as worked examples from lecture tutorial 26. And this will illustrate some of the formulas that we just covered. So first of all, let's take a look at question number 1. Suppose that we have some sort of wheel assembly here that's mounted on a stationary axle at its center. Okay. And suppose that there are two forces that are tugging on this wheel assembly. There's force number 1, which is pulling on the wheel assembly at a smaller radius of only 30 centimeters away from the axle. And then there's force number 2 that's up here at a larger radius, 50 centimeters from the axle. So the one question that you're being asked right here is to find the magnitude and the direction of the net torque on this whole wheel assembly. Okay, assuming that the pivot is right here at the center. All right, well, one thing I want to do is I know that the formula for torque involves both the forces, which are illustrated here already, but also I need to identify what the vector r is for each of these forces. So I'm going to draw the r vector starting at the axis of rotation, or pivot, and going to the location on the object where the force acts or is applied. So this is the vector r1. And up there is the vector r2. Okay, because I see that force 2 is applied up there. All right, now I can ask the question, what's the value of phi in each of these two cases? Well, I can see pretty quickly just by inspection that force 1 is perpendicular to vector r1. So I know that the value of phi is going to be 90 degrees. But just for good measure, let's go ahead and prove that to ourselves, just to really be sure. So what I'm going to do is I'm going to redraw vector f1 right up here. So I'm just redrawing it again. And then I'm going to draw vector r1. So I'm just recopying these two vectors, right? But I'm putting their tails together so that way I can get a good look at what the angle is between their two directions of separation, their two directions. What is the angle of separation between their two directions? So notice in this case that it's 90 degrees. R1 points to the left, F1 points straight down on the page. So I can see with confidence that phi is equal to 90 degrees for force 1. Let's take another look at R2 and F2. So if I think about this direction, or the angle between the direction of R2 and the direction of F2, R2 points toward the top of the page, F2 points to this sort of upper right direction, 60 degrees away from vertical. So I could just try and eyeball it and say, all right, it looks like R2 and F2 are 60 degrees apart. Just to be sure, though, I'm going to redraw them and put their tails together, and that way I'll be able to see exactly for sure what the angle is between their two directions. So I've redrawn vector R2, and now I'm going to redraw vector F2 with their two tails next to each other. And I can now see by inspection that that angle right there, phi, looks like this angle right here. Okay. And indeed, if this is 30 degrees, then that has to be 60 degrees. All right, so now I know what phi is for force 2. I know what phi is for force 1. So that'll allow me to now calculate what the torques are for those two forces. So let's do it. Let's calculate the torques. So let's do it individually first. Torque 1 is going to be equal to F1 times R1 times sine of the angle between the direction of F1 and the direction of R1. By the way, you're welcome to write R1 F1 instead. It doesn't matter. It's just multiplication of the two magnitudes of the two vectors. So this, using the values that are given here in the problem, this is 50 newtons at a distance of 0.3 meters times sine of 90 degrees, which is just 1. So when this is 1, you can also just omit it or just write 1. And I see that this is going to be exactly 15 Newton meters, and it's in the counterclockwise direction. Because all by itself, if I ignore force 2, force 1 right here is attempting to rotate the wheel in the counterclockwise direction. Okay. Now let's calculate torque 2. Okay, using the same values from right up here. And I ask my calculator what that is, and I get 30.31, etc. Newton meters. So this is just carrying a couple of extra digits, right? This may be a 2 sig fig problem, but again, for now, we want to carry those extra digits to prevent round off errors. And I can see that by itself, if I ignore force 1, by itself, force 2 is attempting to create a clockwise torque. So there's trying to create a torque in the clockwise direction, right? So now when time comes for us to find the net torque, I'm going to use my sign convention, plus and minus sign convention, right? For adding torques. So I can find the net torque. That's going to be equal to torque 1 counterclockwise. So I'll make it positive. And then torque 2 is clockwise. So I'll make it negative. So that's going to be positive 15 Newton meters minus 30.31 Newton meters. And the answer is about negative 15.31 Newton meters. Now I say, well, this actually looks like this should be a 2 sig fig problem. So I'm going to go ahead and round that off now to about negative 15 Newton meters. So if I'm asked what's the magnitude of the torque, I take the absolute value of this, and the magnitude is going to be 15. And if I am asked what's the direction, that negative sign, that negative value there means the direction is going to be clockwise. Okay, so that's question number 1. Let's move on now to question number 3. Question number 3 also starts off with summing the torques. And then it's going to, once we do calculate and sum the torques acting on this sort of circular wheel-shaped space station, then we're going to use that net torque to solve a dynamics problem, which is, all right, if the station starts from rest, it's going to now angularly accelerate. So what must be the amount of time that must pass for the station's angular speed to get up to 0.2 radians per second? So that looks like a dynamics and kinematics problem that we'll be able to solve once we get the angular acceleration from the net torque. Then finally, there's one last follow-up question at the bottom, which is, what is the net work done on the space station by the torques during that time period? So that can use our net work equation. All right, well, let's start off here at the top saying, all right, there's 2 thrusters here that are acting on the very edge or very rim of this little space station. So each of these little thrusters creates some sort of force, and we're told that each of those is a force of 40,000 newtons. So I'll call this one F1, and I'll call that one F2. It's just my choice, right? An arbitrary choice. And we know that each of these has a magnitude of 40,000 newtons. So they're really equal and symmetric. And the reason for this is, of course, if one of these were stronger than the other, then the net force on the space station will cause it to accelerate in the horizontal position. All the space station operators want to do is they just want to spin it up, but they don't, at this moment, want the space station to actually move off through space to the right or to the left. So notice how the net force is balanced here, but the net torque is definitely not. So this is not an equilibrium situation, right? And then if I want to figure out ultimately what the torque is going to be for each of these 2 forces, I need to identify what the R1 and R2 vectors are going to look like. So we know that the intended axis or the intended pivot or axis of rotation is going to be the center of the space station. So I'm going to use that as my pivot for calculating the torques. Right? For most of these problems, the choice of pivot or axis will be pretty straightforward. It'll be pretty obvious just from the context of the problem. And notice I've now identified the R1 vector and the R2 vector. Now, in this case, both of these, I think we can identify what the value of phi is just by inspection. So the value of phi here is going to be, technically, actually, it's this angle right here. I should be clear. It's the angle between the direction of R2 and the direction of F2. And that angle is right here. And then here, the direction of R1 is continued by this dotted line, and the direction of F1 is to the right. So therefore, phi 1 is actually there. Okay, technically, that's the proper place to put it. Now, it doesn't matter, regardless in this case. In both of these cases, we can just see by inspection that the force and the R vector are perpendicular to each other. So they're both going to be 90 degrees. All right, so now we can say, all right, for each of the two thrusters, the magnitude of the torque, right, for either one thruster, the magnitude of the torque is going to be equal to the strength of that force F times this length R, which is the same in both cases, times sine of 90 degrees, which is the same in both cases as well. So I'm just kind of taking a little shortcut here, and I'm calculating both of the torques in one fell swoop. So the force and the radius are both given, and this is sine of 90 degrees, which is 1. So either torque, in this case, is going to be equal to 7.2 million Newton meters. And in both cases, I can see that both of the torques act in the same direction or orientation for the twist, and they're both counterclockwise. So in that case, when time comes to add them up, I can make sure that they both are positive. All right. Now I can round this off if I want. I could, this is a case where you could easily just keep the extra significant figure, because you could think of it as gaining a sig fig through carryover of addition. If you think of this as addition instead of multiplication. So either way, this would be a correct answer, or you could think of that as being a correct answer. Great, so now we know the net torque. So looking ahead to part B, how much time must these thrusters fire in this manner with that force in order for the station to speed up, right, spin up from rest to an angular speed of 0.2 radians per second? Okay, and the reason that, of course, that they want to do this is so the people inside are going to feel this sort of sense of artificial gravity. All right, well, if we think about our equations of kinematics for constant acceleration, or in this case, constant angular acceleration, I'm sure that one of those will allow us to solve for the time. I'm thinking of equation number 1 or equation number 2. Both of those contain time. However, they also all require angular acceleration. So what I think we need to do is find out first, what will the angular acceleration be? So first, let's do that. So first find the angular acceleration, and the way we can do that is with Newton's second law. Now, the good news is we just found this net torque up above. We're given the moment of inertia of the entire space station in the problem, and we can now solve for the angular acceleration. So I'm going to put that extra significant figure back in. We're told that the moment of inertia of the entire space station, up in the description at the top, is 2.4 times 10 to the 11th kilogram meter squared. And using that, I can solve for alpha. So alpha is 6 times 10 to the negative 5 radians per second squared, radians per second per second. Now, it turns out this is actually exact. My calculator tells me it's exactly 6 times 10 to the negative 5. Okay. So if it weren't exactly 6, I would carry extra significant figures. Now I can use kinematics, assuming constant angular acceleration or some average angular acceleration, and I can solve for the amount of time it takes. So let's use our first equation of kinematics. There's probably more than one correct way to do this at this point, but I think the first one will be the most efficient. We know that we want to get up to, I know that I want to get up to a final angular speed of 0.2 radians per second, and I know that I start from rest. Great. So using this expression, I can solve for the amount of time it takes. My calculator tells me that it's 3,300, etc., with an infinite number of threes seconds. Now notice all the answer choices here are in minutes, so I'll just convert this into minutes. And I get 55.56 minutes, 2 sig figs on the final answers, so that rounds to 56 minutes. All right. Finally, question C is asking, all right, as the space station spins up from rest up to this final angular speed of 0.2 radians per second, what is the net work done on it by all torques? Okay. All right, well, I can think that there's two ways for us to answer this using either of the work equations that we just covered for a rotating system. One way to do it would be to say, all right, let's use the work energy theorem. The net work or total work done on a system is just the change in kinetic energy of the system. And in this case, the object has no translational kinetic energy. It only spins on a stationary axis. So it only has rotational kinetic energy. So that's going to be K final minus K initial. Now we're told up above that the object starts at rest. So I need a little more room here. So let's expand these two expressions. We know that kinetic energy is I times omega squared. And kinetic energy final will have omega final. Kinetic energy initial will have omega initial. We know we start from rest. So that second term here will be 0. Well, then all I have to do is just calculate the first term. So using the moment of inertia that we're given at the start of the problem, and the angular speed that we know we've reached, which is that 0.2 radians per second. Make sure you square it. We find that the answer is 4.8 times 10 to the 9th joules. And my calculator tells me that the answer, that answer is exact. So it's just 4.8000. There is an alternative way to answer this same question. And I'm going to, just for the sake of completeness, I'm going to show you what that is. You might remember the other definition for rotational work is analogous to the definition for translational work, which is that rotational work done by a single torque on an object that undergoes an angular displacement is equal to torque times the angular displacement of the object times either plus or minus, depending on whether the torque and the angular displacement are in the same direction for plus or opposite directions from each other for minus. Now, in this particular case, either one of these torques is acting in the same direction as the motion of the object, right? As the angular displacement of the object. In fact, these are the torques that are making it move, in fact. So in this case, we want a plus sign for either one of them. So what we can do is we can say, all right, we can figure out what the work is done, how much work, how many joules of work are done by either torque on the wheel as it undergoes an angular displacement of delta theta, if we figure out what that angular displacement is. So let's do that first. So let's find the angular displacement. We can do so with our kinematics formulas. So let's use kinematics formula number 2. Again, there's more than one way to proceed here. And at this point, thanks to my work up in part B, I already know now what alpha is, and I've already found what the time is. So first of all, this first term here is 0 because the spacecraft starts at rest, the space station. And then the second term, I can use the values that I calculated in part B. Make sure you square that time. And I find that in this case, the angular displacement that the space station undergoes from rest to the moment that it hits 0.2 radians per second is about 333 radians. So now knowing that, I can now find what is the torque, the work done by either torque. Well, I think I'll do both with one calculation. So the net work done by either torque is going to be the total work done by both torques, which is going to be torque 1 times displacement plus torque 2 times the displacement. And we already decided that both of these are positive, right? Because the torque, in both cases, the torque is in the same direction as the angular displacement of the station as it turns. Okay. Now, it turns out this is the same delta theta in both cases. So I can pull that out to the side. So this becomes torque 1 plus torque 2 times delta theta. Oh, and behold, that's my net torque, which is the answer to part A, right? So this is just the net torque in part A, okay, which shouldn't surprise me, right? Unlike when we had work problems with forces, forces can point in a diversity of different directions. So it is not necessarily the case that we're going to have net work is equal to net force, magnitude of net force times displacement. Instead, it would have to be some sort of vector sum here, right? It'd be much more complicated. Here, though, there's only 2 ways torques can act, clockwise or counterclockwise, positive. And so that would create either negative or positive signs for clockwise and counterclockwise. So in this case, yeah, it makes a lot more sense that the algebra should just work out nice and neat. So this is 1.44 times 10 to the 7 Newton meters. Okay, and that was in the positive direction, positive sense, counterclockwise. And then delta theta is 333.3 radians from right there. And sure enough, this comes out to be the same answer. So it's again a gain, positive 4.8 times 10 to the 9th joules. So 4.8 gigajoules. So that's an alternative way to solve the same problem. All right. Well, all that leaves for me to model for you right now is question number 4. So question number 4 is sort of a pair of seesaw problems. In both cases, it involves a 40 kilogram child sitting to the left of the fulcrum and a 28 kilogram child sitting to the right of the fulcrum. And the only difference between part A and part B is the 28 kilogram child is initially, you initially know where the 28 kilogram child is sitting, and the system is not balanced. Okay. Whereas in the second case, you're asked where should you position the 28 kilogram child to get the system to balance. All right, so it'll be helpful for me to sort of visualize the situation first to sort of see what's going on here. So suppose that this is the plank of the seesaw. And I guess it would be helpful if I could just sort of name these two children. So we'll call them child A and child B. We'll call this child A. And we'll call that child B. And child A is going to be, now I don't know exactly, okay, we're told that that in this problem, the fulcrum is exactly at the center of the seesaw plank. So that's not going to be the case for every question. In fact, there are going to be some questions where you're allowed to position the fulcrum wherever you want. Right now, so what that means is the center of mass of the plank is right here, right above the fulcrum. All right, so now child A is 1.5 meters away from the fulcrum. So I'm going to go ahead and start labeling some of my vectors here. I already know that this is going to be the vector RA for child A. And I know this is going to be 1.5 meters. And child A has a weight. And then child B, initially, for this first part, child B is, we're told that child B is at 2 meters away from the fulcrum. So that's going to be this vector right here. And child B does weigh less. All right. Now, just briefly, the seesaw plank itself has some weight, right? Now, what does the vector look like for this weight right here? What does the R vector, pardon me, what does the vector R look like for this force, knowing that the weight of the plank is positioned immediately on top of the pivot? Well, we can see that in this case, R for the plank is equal to 0. So the distance from the pivot to the place where F plank acts is 0. There's no distance there at all. All right, so in that particular case, we can already predict that the plank is not going to create any torque about the pivot because the pivot happens to be right underneath the center of mass of just the plank, not the whole system, but of just the plank. Okay, the whole system would be balanced if the entire center of mass of the whole system is right where the fulcrum is as well, and that's not the case for part A. Okay, it will be the case for part B down below. However, just if we consider just the plank of the seesaw alone, we are told that its center of mass is right above the pivot. Therefore, it creates no net torque, and the seesaw plank by itself is balanced. So it's going to create no torque, just the plank itself. Child A is going to create a counterclockwise torque, and child B is going to end up creating a clockwise torque. Also, I can just see by inspection here that the value of phi for both of them is going to be 90 degrees, at least in the current position. If the seesaw were to tilt significantly, the forces are still toward the center of the Earth. The R vectors, however, follow the plank. So then both of the phi values would start to change. One would get bigger and the other would get smaller. But at the moment here, at the moment shown here, which is usually the situation I'm going to give you when there are seesaw problems, we'll assume that it's always this sort of perpendicular situation where the seesaw itself is exactly horizontal. All right, so now let's go ahead and figure out the answer to question A, which is what is the net torque, right, of the children about the pivot. And we've already decided actually that the torque contributed by the plank itself is 0 in this case. All right, so let's figure out each torque by itself individually. So the torque from child A is going to be equal to the force from child A times the length of RA times sine of what will be 90 degrees. Now we know that this force is created by the child's weight. So I can go ahead and call this mg. And now plugging in the values from up above. Okay, so the weight of child A is going to be 40 times 9.8. So that'll be almost 400 newtons times 1.5 meters. And that turns out to be 588 Newton meters. And just for bookkeeping purposes, I'm going to also make a note here that this is counterclockwise. All right, let's do the same calculation for child B. Now, in this case, the position of child B is given. So we know what the value is for this, the length of RB. When I calculate this, I'll get 548.8 Newton meters. And this one is clockwise. Great. So now we can take this information and we can combine it and find the net torque. Now, looking at my directions, I see that torque A is counterclockwise, so I make a positive. Torque B is clockwise, so I make it negative. And if we had a third torque from the plank, we would need to worry about whether it's clockwise or negative or counterclockwise as well. But in this case, we know already that it's 0. It's good to just keep remembering that it is possible for the plank itself to have a torque if it is if it is not centered on the fulcrum, right? If its center of mass is not directly above or below the fulcrum. All right, adding these up. I get that the net torque is about positive 39 Newton meters. Notice I just lost 1 sig fig here due to subtraction. So if this were a 3 sig fig problem up above, which it sort of looks like it is, now our final answer is really down to only about 2 sig figs. So the net torque is about 39 Newton meters. And again, this positive sign here means counterclockwise. All right. Now looking ahead to part B says, all right, you have the same general overall configuration here. The only difference is you're told that the system is balanced and let me say it a different way. Child B is moved to a location so that the system does balance. What is the new location of child B? Well, let's sort of just think about it qualitatively first. We know that in their current configuration, the system has a net torque in the counterclockwise direction. So the entire system wants to, swivel that way, about the fulcrum, that direction. So we know that we can increase the torque that child B exerts to try and make that clockwise torque bigger by moving child B farther from the fulcrum. The alternative choice would be to move child A closer, but I'm not allowing that as an option. I'm saying, suppose you can only reposition child B. So in that case, we need to make child B farther. So already we know that we can eliminate options A and B because those both have child B closer to the fulcrum, and only these last three options have child B farther from the fulcrum. Right? So if you were just asked, oh, which way should you move child B, to the right or to the left? We know the answer has to be to the right to balance the system. Let's find out what the new position is supposed to be for child B. And one way we can do that is by, instead of saying that this distance here is 2 meters, we'll instead say that suppose this distance here is unknown, right? We could actually just call it RB. So, well, here, that's what I'll do. I'll just keep the name RB because that's what we already have a name for that distance. So we're going to suppose in this case now, for the second part of this problem, part B down below, that is unknown. And what we do know is that the net torque instead is supposed to be 0. All right. So what I'm going to do is I'm going to basically solve the same problem backward. I'm going to say, all right, suppose that we know that the net torque needs to be 0 to balance the system, right? So the net torque all right. So knowing that, the torque from child A hasn't changed. And the torque from child B, I'm going to have to revert back to this expression here to make RB be my unknown quantity. So let's go ahead and plug in what we know. So the torque from child A, positive 588 Newton meters. And the torque from child B is going to be 28 times 9.8, which is 274.4 newtons. I didn't show it up here, but this is 274.4 newtons, like the force from child B, times RB. That needs to be equal to 0. Now we can solve for RB. So it looks like child B needs to be 2.14 meters away from the fulcrum instead of 2.0 meters away from the fulcrum. And then that'll balance the system. There is another way to solve this problem, and that would be to say, well, the system is balanced when the center of mass of the two children is exactly at the position of the fulcrum. So we could instead write out an expression for the position of the center of mass of the two children as a system, and leave the position of child B as the unknown in that equation, and say that we know that the answer to the center of mass has to be exactly where the fulcrum is, which would be, say, we have to just sort of like pick a location where where the fulcrum is. We'll say call the fulcrum 0 and put child A at -1.5 and put child B at unknown positive distance or location. And then we could solve for the center of mass that way and see if it equals 0. And essentially, it's the exact same thing that we've just done right here. Because remember that each of these torques right here is a mass times g times a distance. So if we just drop out all the little g's, what we have is mass times distance and mass times distance. So it's essentially a center of mass calculation. And so yeah, that makes good. And it's nice that it makes sense that that should work. All right, so that's the answer to the second half of problem 4. So I'm going to stop there. You can try the additional problems on this particular tutorial, or you can just go directly to the problems in Mastering Physics for additional practice.